uh, about research paper. They were position paper. This time it's technical paper, and it is going to be 5 interesting talk. And the first one is an exploratory study on the usage and readability of messages within assertion methods on of test cases. Quite interesting because touch NLBSE and a bit of testing. And the presenter is, I see online, Tarin, right?
Yes.
Is it you?
Yes.
Very good.
Hello.
Very good. Okay, so if you're ready already, you can start sharing your screen. So we see your slide, and then you can start your talk.
Can you see my slides?
Very good, very well, and also you.
Oh,
Thank you.
great. Thank you. All right. Good morning, good afternoon, or good evening, wherever you are. My name is Taryn Takabayashi. I am a master's student studying under the guidance of Dr. Anthony Paruma. This paper is one of the first steps towards my master's thesis work on assert message usage and structure. So without further ado, on behalf of Dr. Anthony Paruma, Dr. Mohammed Weem Makawer, and Dr. Christian Newman, I would like to present to you our research, an exploratory study on the usage and readability of messages within assert methods of test cases. We are from the University of Hawaii at Manoa and the Rochester Institute of Technology. In our study, we explore the readability of assert messages used in assert statements as our first step in investigating how developers utilize assert messages and the characteristics of how the messages are structured. Unit tests are essential, as we know, to ensuring a software system's quality, and they allow for quick verification of the code performance. Well-written unit tests simplify the process of debugging and make it easier for developers to collaborate on projects. Assertion statements are often used to verify if the output of a unit of code matches the expected output based on the provided inputs. And while the assertion message is optional, it can provide useful feedback to the developer in debugging errors in the production code. So there is current research that exists on the best practices when writing unit tests, but a largely unexplored area is the utilization and readability of the assertion message within an assert statement. But assertion messages can be imperative for developers who did not originate the code to comprehend both the test case behavior and troubleshoot any test case failures. Developers are free to have multiple assertions within a test case, and they have no restrictions in constructing their messages. So that, though, is a problem in that while a message may be understandable to the author, that is not necessarily the case to the external developer or a new team member. So the first listing we have here is readable and descriptive. We can clearly see why the test case is failing. On the other hand, listing 2 is understandable as 0,0, but it is unclear why this set of numbers is important and unclear how it relates to the test case failure. So our exploratory study is the first step in investigating the benefits developers gain from assertion messages and the developer's mental model for creating and comprehending these messages. The goals of our study are to investigate the extent to which developers utilize assertion messages and analyze how these messages are structured. Such knowledge should support the development of tools and techniques aiming to determine the quality of assertion messages and support the auto-generation of test cases with easily understood messages. We investigate the following research questions in our paper. Firstly, how often do developers use messages in their assertion methods, and in what ways are these messages related? This will allow us to group messages into high-level categories. Secondly, to what extent do developers provide easily comprehensible messages in assertion methods? We utilize existing readability metrics for this to analyze different categories of assertion messages. We aim to provide developers with this a set of guidelines on crafting readable and understandable messages. Our results represent a preliminary yet significant step towards increased awareness of assertion messages. And through this, we also provide a data set of assertion messages so that our research may be extended and replicated. In our design, we analyzed the most recent releases of 20 open source Java systems with a JUnit 4 testing framework. We specifically chose these systems because they were used in prior unit test code related studies. We used the IntelliJ platform SDK to detect test files in these projects. For all detected assertions, we extracted the assert method, the containing method, class, line number, and if the containing method is a test method. To better understand each message, we manually reviewed all of the messages, assigning them to one of three categories: identifier, string literal, and combination. We leveraged the Flesch reading ease and Flesch Kincaid grade level, which are well-established English test readability metrics that have been utilized previously in other code readability studies, including code comment comprehension. We used the perceptron tagger in Python's NLTK package to generate part-of-speech tags. And finally, we examined the extracted data to answer our research questions and provide representative samples. So the three categories of assertion messages we found were string literals, which are a sequence of characters enclosed in double quotation marks, identifiers, which are the value of an identifier such as a method call, a constant, or a variable, and combinations, which are a combination of string literal and identifiers. We identified 31,063 methods with JUnit assertion statements, but less than 6% of them contained one or more assertions with an assertion message. Focusing on individual assertion statements, there were a total of 86,321 JUnit assertion methods, but only 3,872 or 4.49% of the assert methods contained an assertion message. Although every project contained assertion methods, only 11 out of 20 had assertion methods with a message. So all in all, this indicates that assertion messages are underutilized by developers. Next, we examined the type of assertion method that frequently included an assertion message. The majority of these messages were found within an assert equals or an assert true method. By analyzing the unigrams and bigrams of these messages, we discovered several common words. For example, the phrase does not was frequently employed to indicate that the expected value did not match the actual value for assert equal statements. Should and toString were also frequently used to express what the expected value was supposed to be. We classified the messages into three main categories: string literals, combination, and identifier. String literals were the most common type, followed by combination messages that consisted of strings combined with identifiers, and finally, identifier-only messages. There seemed to be a preference for using strings combined with variables in combination messages, while identifier-only messages tended to feature method calls. In summary, developers often omit assert method messages when explaining test case failures. When assert messages are used, they are commonly found with assert equals and assert true statements. Additionally, we observe that developers tend to employ similar terminologies in their messages, and the messages follow three common patterns. In answering our second research question, our analysis revealed that string literals were the most frequently used type of message, and they tended to be easy to read. Messages containing only identifiers were also easy to read, but they may not be as understandable to those unfamiliar with the code base. On the other hand, messages containing a combination of strings and identifiers often resulted in low readability scores, likely due to their length and the usage of domain-specific terminology. Combination messages that are shorter in length typically receive high reading ease scores. However, some of these messages can be difficult to understand due to the lack of context provided by the identifiers. Similarly, single word string literals tend to have high readability scores, but also tend to lack context. As a result, it may be challenging to rely solely on standard readability measures to evaluate source code readability. Messages composed of string literals often begin with a noun or a complete subject consisting of an adjective and a noun. And this, we found, aligns with the typical patterns of English speech usage. So in summary, readability techniques show that assertion messages made of string literals require a fourth grade education level and often follow a similar grammatical pattern to English sentences, starting with a subject or a complete subject. String literals with single common words or messages with identifiers are easiest to read. However, without further contextual cues, these types of messages may hold little meaning in the fixing of test case failures. So in our takeaways, we found that developers frequently neglect to include messages with their assert statements. And even when they do, there's often common code smells that appear repeatedly. Thus, there is a pressing need to promote the use of these messages and offer guidance on how to avoid code smells in such messages. Moreover, it is necessary to develop specialized models and tools to process combination messages effectively. This is because there's often a discrepancy between the readability and understandability of messages, which presents a unique challenge for models based on English prose. Through this study, we also identified several code smells that commonly appear in assertion messages. The first is when the message fails to indicate the expected outcome. The second is when the message misleads the developer regarding the cause of the test case failure. And the third is when the message is too brief to provide sufficient context. Developers can utilize this catalog to avoid code smells in their assertion messages. As part of our future work, we plan to conduct a user study to document how students are able to fix errors in production code based on unit tests. We will use their feedback to validate our empirical findings and gain insight in how we can evaluate and recommend high-quality assertion messages. And with that, this is our presentation. If you have any questions, please let me know. Thank you.
Let's thank the speaker. Any question for Tarin? Very good, Sebastian, you're fresh.
So what I frequently do in log messages, at least, is often they have a common string, and then I move that to a string called base message or whatever, and I'm suspecting that this could also happen for asserts. How did you handle that in the analysis? Basically, you would have the message and then concatenate it with something that changes across the asserts. Would you consider that as having a string literal or not? So did you resolve those cases basically? where this literal was not part of the assert, the string, but it was basically outsourced.
Yes.
No?
So I think that falls under the category of our combination messages. So let's see if we can just scroll back here. Yes, so that would be combination messages. So yes, those were one of the categories that we identified, and they are something that, so they are something where, yes, it's something that makes sense to the developer, but maybe someone who is just new to looking at the code, it might be more difficult for them to figure out what the actual thing is, or but in other ways, it can also be useful, I suppose, to the developer where they're like, okay, this is just something that might change. So I just want to say this plus this plus this. And so we can also see the reason why they use those messages. So again, an exploratory study. So we were just kind of trying to categorize the different messages. And so are they just strings? Are they identifiers? Is it a combination? For example, if it was just an identifier message, that would be more problematic than a combination message. Because identifiers, it would just say something like this, right? Where it's like, there's like no context. It's like, okay, so message. So you would have to really dig down deep to figure out what it is that the developer was expecting from that. Thank you.
We can thank the speaker for answering the question. Thank you, Tara.
Thank you so much.
So the next speaker is, we know him, Christopher Trudeau. And the paper is Top Words for Processing Software Engineering Documents. Do they matter? Actually, it's a question I was really curious about in the past. So thank you very much for investigating this. So the floor is yours.
We're just making sure that remote people can also see the presentation.
Yeah, they see it. They can sleep, on the other side. You never know. It's 4 a.m. for many of them. We see it.
All right. Thanks for helping with the setup. Very good. So this is work that Yao Fan led. He did a Masters of IT project with us at the University of Melbourne. This is just a one-semester project, basically the equivalent of one course. So quite pleased that we managed to get a publication out of this work, and in collaboration with Chetan Arora, who is now at Monash University. All right, the question is really very straightforward. And if you've ever had me as a paper reviewer, and I think some of you may have, and you included a stop word list, or you mentioned that you excluded stop words from your data set, but didn't tell me which stop word list you used, I probably would have asked a follow-up question. Because at least I think in terms of being able to reproduce the results, if you just tell me that you excluded stop words, I wouldn't know how to reproduce this because we don't have a universally agreed stop word list. But I think whenever I asked that question as a reviewer, there was also sort of this nagging doubt in the back of my mind. Does it actually matter? Or would any of the sort of commonly known stop word lists have kind of, led to the same result? And I should just stop asking about such details. That's exactly the kind of question we wanted to ask and to answer in this work. So a few words about motivation, although I think it's pretty obvious probably to the people in the room. For many natural language processing applied to software engineering tasks, so many of the things we've been talking about here, we know that removing stop words can improve things. It's not necessarily guaranteed that it improves things all the time and everywhere, but the removal of stop words is one of those pre-processing steps that we often do when we apply natural language processing to some software engineering tasks. But at the same time, the impact of that removal is kind of under-researched, I would argue, right? Many of us do it. Sometimes we forget it and it still seems to kind of work. So we didn't really know whether it needs to be done. And a lot of the stop word lists that we frequently use, such as the ones published by NLTK, that I'm pretty sure is only being used so much because it's really easy to access and download, is obviously not software engineering specific, right? It's published just as part of NLTK. And we know that the semantic importance of each word can actually differ quite a bit based on the domain. Even, you know, the meaning of words differs between domains. My collaborator Martin Robillard likes to use the example of ant, right? Ant for most people in the world is an insect. For most people in this room, you probably thought of the build tool before you thought of the insect, right? So words have different meanings when we're using them in different domains. We know all of this. So the contribution of this work is then basically twofold. For one, we investigated the impact of different stop word lists or no stop word lists on model performance for 3 papers that we found out there that were really easy to reproduce. Well, actually, I'll say a bit more about that in a few minutes. So we applied existing stop word lists and then checked how do different tools react when we give them different stop word lists. But we also created our own one, or actually we created 2 different versions of them. And we'll go into more details on this. So in general, and you'll see the references at the bottom of the slide there, stop words have been around for a long time, right? So the earliest publication I have on the slide was in the late 80s. I'm pretty sure that was not even the first mention of stop words, but I think that was one of the first bigger lists of stop words that was published. And since then, people have been developing more and more stop word lists. Different people use different ones. They don't always know why they use one over the other. And you see some of the words in this particular tag cloud there have nothing to do with software development. Well, people have a lot to do with software development, I will say that. But some of the other ones probably have a bit less to do with software development. And the fact that stop word lists should probably be used with a bit more thinking about when they will be used. We're not the first ones who thought this. So for example, on Twitter, there has been analysis that found that the Twitter specific stop word list produced better results on some downstream tasks. I forget which one now, but that, you know, Twitter specific stop word list work better than just a general purpose stop word list. That's sort of the related work on comparing the performance of existing stop word lists on new tasks. But there's also related work, of course, on how do you create a stop word list. And the way it's typically done is, I won't go through all the details here in the interest of time, but basically things like TF-IDF, you know, the most frequent words, but most frequent words considering not necessarily the ones that are really important in those documents. And in many cases, the most frequent words are actually the ones that will end up being stop words, but often there's, and maybe that's, can I highlight? Yeah, maybe that's the important part. There is usually some human evaluation involved. So you use something like term frequency and or term frequency and document frequency as a starting point, but then there's still human evaluation. And that's basically the process we used in our work as well. So that brings us to the next interesting challenge here. When the master student started working on this, like I said, it was a 1 semester project equivalent of 1 or 2 courses. I'm not even sure right now. I basically told him, well, you know, go look for existing software engineering tools out there that use stop word lists, make them run and replace the stop word list with a different stop word list. Now, our community doesn't always do extremely well when it comes to producing reproducible tools. I see some knowing smiles in the area. So that actually turned out to be way more difficult than we were expecting. And let's see which of the authors is in the room to make sure I don't overstep boundaries here. So this one, for example, we were not able to get the exact results for, but we were able to rerun it. So that was good. Unfortunately, when we reran it, we didn't get the same results that they report in their paper. Having said that, for our research question, do stop words matter? We didn't necessarily need to be able to reproduce them exactly, but we wanted to see how can we reproduce it, but with different stop word lists. So this was app review classification, paper by Walid Malaysia and colleagues from 2016, empirical software engineering. Don't need to go into a lot of details on this, but as the title suggests, they use app reviews as input and classify them in one of 4 categories. Then I'm glad the author of this paper is in the room. That was the only one that just worked. Well done, David. Thank you. That's how reproducibility should be done. And I didn't know you were going to be in the room. I would have said this anyway. So this is automatic query reformulation for code search using crowdsourced knowledge. And the tool is called RAC. It provides a list of relevant API classes for natural language queries. It has a stop word list there. The student was able to run it within a very short time frame, was able to get to the point where the stop word list is called, could replace it with other stop word lists, could investigate the impact on the performance. And before replacing, we managed to reproduce exactly the same numbers that were reported in the paper. Fantastic. The other one, the paper by my co-author there, Jijan Arora, that one we had to rely on him to reproduce because it relies on industry data. So we weren't able, as non-authors of the original paper, we weren't able to get our hands on that code and that data. But he promises me he followed exactly our instructions to rerun everything, send us the data. I have to admit, I've never seen that data except in the summarized form we have in this NLBSE paper. So those are the 3 tools that we tried. And we also tried a bunch of different stop word lists. We'll call them, for simplicity, very small, small, medium, large. Names kind of give away what the distinction is there. They are from different sources, in particular the rank NL one I see often used in our community as well. So that seems to be one that many of us come across regularly. MongoDB publishes its own, Azure apparently publishes its own, and finally the large one comes from a different source. So we tried these 4 on each of the 3 tools. And we also developed, we tried this one as well, which is also from related work, but from a related work that claims to be specific to the technology domain. And then we built ourselves 2 new ones, one just based on the most frequent words, based on some distribution, and one based on TF-IDF for a Stack Overflow corpus. So we used a large Stack Overflow corpus. We downloaded Stack Overflow questions for particular tags. Details are in the paper. So let's get to the results then. For app review classification, Walid Malaysia and colleagues tools, the original results are always in the top column here. You don't need to read out all the numbers, but the colors basically mean that the green stop word lists, or no stop word list up there, means we got better results, and the red one means we got worse results than the original. So takeaway message just from this, based on the general purpose, these are only the general purpose stop word lists. In the majority of cases, just using a different stop word list actually led to better results. And then if we use the software engineering specific stop word lists, actually the picture is fairly similar. In all but one metric, our TF-IDF list at the very bottom managed to outperform the results that we got with the original stop word list. So already here we see that using different stop word lists obviously makes a difference. And in quite a few cases, it seems to make a positive difference. So if you're ever really close to that result that you want, maybe just play with different stop word lists until it works. Is that good advice? I don't know. On RAC, so the tool by David Lowe and co-authors, you already had the best non-domain specific stop word list. We tried all the other ones. We got worse results for all of them. So in this case, we were not able to outperform your results with another general purpose stop word list, but the domain specific software engineering stop word list curated based on Stack Overflow managed to get another %, I think, out of the data. So not a big improvement, but a slight improvement there. And also gives us a first hint or another hint again that using domain-specific stop word lists seems to be worth the effort. And the last one, this is Chetan Arora's requirements analysis tool on change impact. Apologies, the table is laid out differently now. So now the original is in the first column, and then each row is a different stop word list. Again, you see some green and some red for the for the general purpose stop word lists, and only green, or in one case, the same result in the domain-specific stop word lists. So again, we were able to, by just replacing the stop word list with a different stop word list, to increase performance a little bit. Let me summarize this a little bit, and I realize this comparison is not ideal here, because we had a different number of performance metrics for the different tools. So actually, if we go back to this, you can see that in this case, we had basically 3 data points for to look at for each stop word list. For this one, had 4 data points, top 10, MRR, MAP, and MRK. And for this one, we have many more data points. So if we look at precision recall, F1 measure for each one. Probably shouldn't sum them up. I do that here anyway for simplicity. Just to summarize, which of the stop word lists tended to lead to better results overall. For 17 out of the 19 performance metrics across these 3 tools, our domain-specific, based on TF-IDF, our domain-specific stop word list managed to get us slightly in many cases, but it managed to get a better performance. Only in one case did the performance go down a bit, and in one case it was the same. Interestingly, no stop words generally did not do well. So I guess the general advice here is, unless you're doing something that's very different from the 3 tools that I talked about, chances are stop word lists are probably a good thing. Even with the general purpose ones, we generally manage to get slightly better performance on average, and even more so with the domain-specific ones. Brings me almost to the end of my presentation already. So general stop word lists had varied effects. Some tools show small changes with these general purpose stop word lists, and the software engineering specific ones tended to have the best performance. And that's the one thing, actually one of the 2 things I'd like you to take away from this. Blind use of stop word lists may negatively impact algorithm results. So if you do use a stop word list, think for 5 minutes about which one should you use. Should you use one at all? Which one should you use? And document which one you're using so that others can reproduce the work. And the other takeaway message, data, of course, is online. And importantly, all our stop word lists are online as well. So go to our online appendix on Zenodo there. Take a look at the stop word lists. Feel free to reuse them. That's why we're publishing them. And yeah, now I finally have an answer to the question whether I should nag authors in the reviews that they should mention which stop word list they used and why they used it. That's the end of my talk. Thanks for listening.
Thank you, speaker. There is already a question. Very good. Alexander.
Thank you so much for your talk. So it seems that you are labeling as better whenever you have a number which is higher. But the difference between 82.5 and 80.2 kind of seems negligible. So if you are a bit more critical or /lazy, in a sense, would it make sense to add those stop words if without stop words you are getting roughly the same performance?
Good question. For this paper, we didn't push it as far as looking at effect sizes and so on to really characterize how large the effect is. I'd have to go through the tables now to find where it made the biggest difference. Having said that, we seem to be in a field now where we're often pushing from 80%, where we're sort of step by step pushing from 80% to 90%. And I mean, you could argue the same thing for many other pre-processing steps that we're doing, right? Does it make sense to remove code snippets from our artifacts before we give them to natural language processing, for example? I'm assuming the results would be fairly similar. Taken together, all of these things will make a bit of a difference. So I take your point. I think my main takeaway message is really, it does matter which one you use. Don't just assume that you can just download a random list and don't even tell the reviewers which one you're using. At the very least, it makes your results not reproducible, not exactly reproducible if you don't tell us which one it is. It does make small differences in some tools, and so others it was a little bit larger. And I'm sure there's also more fine-tuning we could do with the stop word lists. That wasn't necessarily the purpose of this particular paper. Thanks.
It's a very nice work and presentation. I have a question about I think some of the works use like more vector space models, and maybe the stop words are more commonly used there. But I also wondering, like the like large language models, what is the impact of stop words? I wonder if you have done some studies on that. Like, is there an impact on stop words, keeping them or removing them?
Yeah, not yet, unfortunately. I think it's a very good question. Thanks, David. I think I fully agree. I think the impact that we're seeing is probably partly because the tools that we reproduced were not from the last 2 or 3 years. So I think large language models may have taken care of some of these differences, and they are probably smart enough to filter out some of these stop words, not explicitly, but kind of implicitly in there. Well, reasoning is the wrong word, but in their probabilities, basically, right? So I think it would be really interesting to replicate this with some more recent tools that use large language models. Yeah.
A quick question. You mentioned previously that when stop word lists are created, you have the human evaluation step, but you didn't do that for the domain specific ones, right? You just did it based on.
If I remember correctly, we actually did. Yeah.
You did.
I
Okay,
glanced
that's good.
over that detail.
Okay.
Yeah.
Okay.
We didn't go all the way with the inter-rater agreement and so on, but we did do a bit of curation
Okay.
to kick out some things that we thought were not stop words, but carried a lot of software engineering specific meaning.
Okay. Thanks.
Other questions? Any remote question online there? Okay, seems not. I will have.
Yes,
there
I
is
have
one.
one.
Go ahead, Andrea.
Out
Very
of
good.
out of a curiosity, which is the case? Did you investigate the motivation behind the worst case in the when you use the SE domain stop words?
Not specifically, but that's a very good question. Thanks, Andrea. I think in many cases, this is a more generic answer because I don't think we looked at that particular case in detail. But in many other cases that we saw, we could often trace it back to particular words that were in the stop word list where it's like, oh no, that's actually meaningful. So I think a good example is the word not. Right, not is fairly common in the English language. Therefore, it has actually found its way onto some of the stop word lists. But for some of these software engineering specific tasks, you know, whether something is the case or is not the case, that's what makes all the difference. So I think it's words like that that have slipped through and sometimes get filtered out by these stop word lists.
Okay, thank you.
We just take advantage that there is next speaker coming, but just as a request, we are always looking for new challenges. Since you already managed to replicate and having things running, if you can contact me or Andrea to have some of the tool that you have experimented as potential new competition. Not sure next year, but we are looking for this type of study, big data set with classification model, or pre-processed, also optimized already. That would be nice input for us. So if you can follow up.
Absolutely, I'll do that. Thank you very much. Thanks.
Let's thank the speaker. So, okay, next, as you see, probably already online. The next speaker is Adriano Torres. He's presenting the work Applying Information Theory for Software Evolution. So we move a bit in a slightly different direction. And, Adriano, the floor is yours.
Good evening, everyone. Thanks for joining. Yeah, we're applying, as mentioned, we're using information theory to gauge how software evolves from a word-based standpoint, primarily. Our main motivation is that as software is created and functionality is extended, essentially we are adding more words in certain positions in the code that are meant to express behavior. And so as more functionality is present, there's more vocabulary in the source code as well, whether it's the code itself or the comments that accompany it. And also because there's ongoing research right now that hypothesizes that there's a very high level of naturalness in source code. So our vision in the end is to be able to detect whether changes introduced to a project deviate too much from what the project is currently expressing, because that could be, in some cases, surprising. Not that it's necessarily bugs or wrong code, but this could throw maintainers off. And also because given that as projects evolve a lot and a lot of information comes through code to maintainers and reviewers, we need to automate ways to separate when they need, where attention should go from maintainers. Otherwise, it's quickly overwhelming to review much code that's generated. So let me give you an example where we start with the basic calculator on real numbers. And let's say we have a commit that, extends functionality now to also allow us to multiply numbers. For us as humans, essentially the most important fact here is the multiply word that was added to the program's vocabulary, in a sense, even more so than the multiplication symbol. And the structures of the code, they're now redundant from an AST perspective, right? Because we're taking two parameters, producing a third value of the same type and operating, making a binary operation. Now, let's say that a maintainer, for some reason, just as an extreme example, decides to make string comparisons in our calculator. So it's natural to wonder, should this be here? Should I be seeing these many occurrences of string or length? Maybe yes, possibly not. But again, that deserves attention from a maintainer's perspective. And now we have a case that's more in the middle, where we are introducing an operation that is on real numbers and produces a number, and it belongs to a calculator, but it has a structure that is a bit more complex, operates on a single parameter, and has a more complex structure associated to it. So even though it should be there possibly, but it's still worth attention. Our contributions here are to define this idea of AST entropy based in the edges of the AST that compose the code. We're going to correlate it to an already existing metric of token entropy. We are going to measure the way that tokenizing the code impacts the overall information content, meaning what happens if we consider all the words, what if we remove language-specific keywords, then we remove numbers. We are going to correlate these metrics of entropy with classic complexity metrics like cyclomatic complexity, number of lines changed, and token count. And we're going to start an investigation on gauging how information content evolves in a project by measuring these sorts of entropy. Contribute to us detecting surprising or unexpected events. So the way we are calculating our histograms are basically in the right side is by computing the AST and then performing breadth first search and connecting all the edges. And in the right-hand side, we're using tokenization methods for identifiers present in literature available as open source library in Python, which splits up the identifiers in the elementary words. The definition that we're working with here is the Shannon entropy, and wherein we are applying, we're taking the frequency of an edge or a word as a proxy for its probability, and then multiplying it by the log, which gives us a representation of the information content in terms of bits, essentially meaning how many bits do I need to represent this blob of tokens that you gave me. Here we have an example of a regular curve that's generated when we traverse all the commit history of a project from its beginning to today. And we can clearly see that, first of all, the information content is ever increasing, but even more importantly, and this was present for all projects that we analyzed, spikes are very frequent. And in some cases, they are almost extreme, meaning The project now contains twice as much information than previously within a single commit. The next picture depicts an attempt to spread this information through units of abstraction, in this case, files. And for this project, we see that the graph pretty much continues the same, which may be an indicator that there's not much complexity management going on in the project. Here we have another example where, again, the information is always increasing. We can visually see spikes, even though the curve is a bit smoother than the previous one. Now, this project here makes attempts to do a bit more complexity management from this standpoint, because you see that after an initial evolution, the spread of information throughout the files sort of stabilized. And this is in accordance with Lehman's law of software evolution, which says that the complexity is going to increase unless there are active efforts to keep it under control. We computed for the 4 essential ways of calculating the entropy, AST and 3 per tokens. We calculated the correlation matrices between these metrics to realize that they are very strongly correlated for most projects. Here's the result for all the 25 high-profile Java projects that we traversed. And we see that the profile is very similar for almost all of them, but in 2, we see that the white squares there mean low correlation between structural entropy and word-based entropy. And when you go there and inspect these projects, you see that they are essentially interface definitions and abstract methods, and they are accompanied by lots and lots of natural language tokens as comments, in a rare case where the comments are more essential than the code, because they describe how the code is to be implemented and integrated. So again, strong correlation between the token-based and AST-based methods. Now, when we move to correlations with classic complexity metrics, the rows to the bottom, we see a more uniform trend in that the correlations are very weak and moderate at best, especially with token count, but even so with cyclomatic complexity, meaning potentially that we can there's a way of approaching complexity that we can gauge with entropy that maybe we cannot with the current metrics. And then when we decided to analyze the spikes that were visually present in all of them, we found that there's a relatively high frequency of them, ranging from 3 to 12%, meaning in about 7 or 8% for most projects, there are cases where the entropy increases by 40%, or like in this example, 300 files are changed. We have more than 300,000 deletions or additions, which are clearly cases where, first of all, they need attention almost by definition, because there's too much information coming in or going away. And also this warrants the need for tools that allow us to gauge what is the impact of this, because clearly a human is not going to be able to say, hey, it's not very impactful, or it's really impactful to delete all these many lines from the code. So we conclude by, our realization that structural and AST and token entropy are very correlated, which makes sense because in the end, the act of coding can be reduced to positioning tokens, words, in the code in certain positions. We, again, noticed that specifically with cyclomatic complexity, the correlations are very weak. And so we can learn facts about the complexity of the projects just by assessing the information content of the words instead of the positioning or the control flow graphs, for instance. We see that different projects have different approaches to trying to spread information over the different units of abstraction. And this could assist us in quantifying impact of complexity management approaches like refactoring. We could assign numbers to how impactful and they were, as opposed to being opinion-based, which they frequently are. And again, we see many cases, 3 to 12%, where there's too much variation in the information content. So these are frequent and impactful. So going forward, we're seeking to automate the process of assessing how impactful this could be and how much attention it needs relative to everything else that's happening in the project as it evolves. So I'll leave you with this. So feel free to ask me any questions or shoot me an email to my very short email address if you need anything.
Hidden there and down. Yeah. So let's thank the speaker. Adriano. So there is any question for Adriano? Don't be shy. I have one. Maybe also line. Have someone is thinking about it. More generally, when I look at your presentation, first of all, wow, interesting. No, and I never seen a study like that. It's quite novel. And I was also relating to some research is more slightly related, which is change analysis. What happens within commits? And within entropy, you can measure what happens during software evolution. And I was wondering or asking myself how the notion you're using is related to previous notion of complexity or change metrics over software evolution, and or if you are going to investigate that, if they're complementary, different, similar.
My idea is to eventually be able to see if we can complement that. We haven't been able to get that just yet because we were just playing with these definitions in this work right now. But eventually we want to see how they integrate and how they overlap and how they can express something that the other one cannot. But we haven't done it just yet.
No, it's okay. If I can follow up and no one interact me. Let's say, I was curious how generalizable it is to other languages, or other,
Good
because
question.
it seems to be quite generic. So you can,
yes,
but compared to other approaches like a very low level specific, seems to be more generalizable, which is, I think, is winning argument.
Apparently, yes. We could notice when we inspect the graphs more closely, you can see that the effect of keyword reserve, and numbers is very low. It doesn't impact the overall trend. So one would imagine that the words are the defining factors. So they should be language agnostic to some extent. It's in the plan to eventually use tools that are able to pass multiple languages
Very
to
cool.
come to this realization. But apparently, yes, for these 25 projects, and it was a decent amount of data. Apparently, yes.
Again, if no one interact or raise an hand, I had the last question. So now you have a nice theory. What will be the application scenarios? Now you invented a theory if you want, but there are many tasks you can use for, concrete ones.
Right.
I don't want to mention, maybe you have something in your head, but how you plan to use that for a concrete development task, for example? What would be the first you will
Great.
apply to?
Being myself a practitioner, I still work in the industry to the day. I would want to integrate this in deployment pipelines, just like we do with software testing before code reaches production. I'd want to have a step in the pipeline that says, hey, there's your changes generated this index of potential complexity or surprisal, if you will. So do we want to move forward with the change? Do we need to discuss the change further? But yeah, I'd want to integrate it into actual software deployment.
Very cool. Anyone online there?
I have a question.
I knew it. Good. Go, Andrea.
Thank you. Thank you for your presentation. My question is simple. To what extent are the entropy investigations affected by code rebase? Is it a problematic case, code rebase, or not?
Could you elaborate a bit on what you mean by code rebase? Do you mean rebasing a commit?
Yes, very large changes, very large commits.
Well, yes.
With many changes, deletions or additions, and so on.
Well, it is actually depending. Again, it's going to depend on the. Let's keep it simple.
Of course.
it's going to depend to how many new words or how much the frequency of the words in the source code change after the rebase. So if the histograms, the distributions are sort of preserved, then this should be a low indicator for surprise or an unexpected event. But this is unlikely for the commits that I analyzed manually. Whenever there were rebases or many lines added, there would be a high relative introduction of entropy.
Okay. Okay, thank you.
You got another question. You're very popular, you know.
Are supervisors allowed
Being
to ask
a
them?
co-author. No, if I understood the question correctly, it was also about whether in a commit a lot of lines of code change, whether this is related to changes in entropy. And we've not looked into that in this paper, but Adriano has since. So maybe you can comment on that as well.
Yes, absolutely. Yes, we ran correlations with a number of lines changed and the entropy distribution, and there seemed to be no strong correlation for all the 25 projects that we analyzed. So they mean different things essentially. We can have code that changes a few lines but introduces a lot of entropy in that file, but we can have the other way around too.
Okay, thank you.
See other resident online so far, but I have 1 year. Very good.
Thank you very much for great presentation. Do you think over time something like this could be also used as some kind of metric that indicates the quality of some projects or something like that, or at least when you analyze it over time, how this changes?
Right. So as it is right now, not much, because we're not analyzing, for instance, we're not analyzing things, how big a method is, or how levels of nesting, etc. Things that, for instance, cyclomatic complexity captures. And the way this is going, apparently, at least to my eye, is that we're going to drift ever more towards this word-based analysis, as opposed to questions like this, like code structure. But certainly, this can be a gauge to code quality, because if you take a histogram of the file and you know there's A, B for of names of variables that don't convey meaning, then there can be some overlap. But I'd say that generally no. Thank you.
Okay, so I think we can thank Adriano again one more time. So the next two presentations are going to be online. So just expectation management. So you don't see people coming in the stage here physically. Also to give Sajjad some time to set up the online. The next speaker is Mohamed Latif Siddiq, and he's presenting zero-shot prompting for code complexity prediction using GitHub Copilot.
Hello. Can you see my screen?
Yes, we see you, we hear you, and we see your slides. We just put, yeah, exactly. Very good.
Thank you.
Ready to go.
Hello, everyone. I'm Mohamed Latif Siddiq. I'm from University of Notre Dame. I'm a second-year PhD student here. I'm going to present our work, zero-shot prompting for code complexity prediction using GitHub Copilot. Code complexity, runtime complexity is extremely important for practitioners. It gives an idea about how long a program will run, which is directly related to the performance of the code, but also of the software. And in our study, we're going to use GitHub Copilot to do that. GitHub Copilot is a code generation tool which can understand the code. We leverage this idea to use an prompting technique to classify different code complexity. So what is the zero-shot prompting and zero-shot prompting? It is an introductory tweet from GitHub about GitHub Copilot. It is published in release in 2021 and integrated in various IDE like VS Code and JetBrains tools. So here is a prompt like they give a function signature and GitHub Copilot can automatically generate a source code for you. So what is G-shot prompting? In G-shot prompting, there will be no further example about the tags. So then the few-shot prompting, there will be some examples like there is a function signatures and the complete functions, and it will help the code generation models to carry on the tasks. So in our tasks, we are going to using GitHub Copilot. It is based on Codex model. Codex model is a descendant of GPT-3 models, which recently powered ChatGPT, a hype tool published last year. So what is computational complexity? Computational complexity means time taken by computer to execute an algorithm considering the input size of n. For example, if an algorithm has a time complexity of order of n, this means the number of operations could increase linearly with the size of the input data. If the input size doubles, the number of operation recursions also doubles. Order of n actually indicates the higher limit, upper bound of the runtime of the source code. So here's an example of binary search, which actually takes logarithm complexities. So in our work, we collected data set from Gion et al., where we classify 6 classes: constant class, linear, logarithmic, quadratic, cubic, and linear algorithmic, and NP-hard problems. And number of samples in the test set is around 13% to 15%. So in our case, we point in this way. This is the context of the class which we're going to classify in a particular complexity class, and then give a prompt for the GitHub Copilot complexity it comment to fill up the complexity for that. We evaluate our result with accuracy, precision, recall, and F1 score. We use micro average for calculating F1 score as our data system balance. So for the results, we compare results with different machine learning-based technique, neural network-based technique, P10 with the P10 model, fine-tune P10 models, and GitHub Copilot. We can see that for the linear complexity, GitHub Copilot perform better than others, but other technique actually perform better than GitHub Copilot. So here is the result for top one and top all. Top all means sometimes GitHub Copilot can give you more than one suggestion. It can be up to 10. So the correct complexity may be not be in the top one, maybe in the top all. So when we compare that, we can see that top one has accuracy around 45%, where in the top all there can be a correct solution, correct class. It can be up to 56.38%. So here is a confusion matrix of communication using top-one suggestions. Here, -1 means actually GitHub Copilot sometimes give you output from different classes, like we're consensus classes, but it can output you different classes. And we can see that for the NP-hard problem, it's sometimes confused with the quadratic complexities. For cubic, most of the time it is classified with any quadratic complexities. So what our main findings here is like, yeah, for in the top one suggestion, it can be carried by 45% times. If you consider all the suggestion, it can be 56% times. It outperforms linear complexities. But our finding is that it is not better than most of the machine learning, other machine learning based techniques. It can be perform better if you can use few-shot prompting or chain of thrones, other prompting techniques. Thank you.
Let's thank the speaker, Omet. So, a question from the audience here or over there? It's not. Or, no. Here I was more reading your talk. I was more curious, more on fundamentally, you have presented results which are quantitative. No, there is a question. I would like to give Andrea first, the floor. Andrea is over, and then I will jump in. Go ahead, Andrea.
Okay, can you hear me?
Yeah, I can hear you. Thank you.
Okay. My question is about top 10 suggestions. What do you mean with top 10 suggestions? That suggestion is the complexity.
Yeah, different complexity classes. So yeah. Okay.
How many classes are there? you consider it?
Yeah, so we are actually considering 6 classes. In our train set, the ground truth is divided in 6 classes, but GitHub Copilot 10 GPT-3, and it can output different classes out of our class distribution. Like you can see there is no any square log and complexity there in our train test set, but it can give you that type of classes.
So basically, the response is all classes. Right?
Yeah, it will give you a class for that particular class, particular composite class for you.
Okay. In
Are you satisfied, Andre? Or?
did you?
Okay, good.
Yeah. I have another question. Did you envision some kind of application in which this could be useful for developers?
Yeah, of course. Actually, it mainly focus, I think, for the competitive programmers. They have to solve different kind of competitive programming problems, so that can be useful for them. And yeah, I think and it is for prompt engineering, you need not to fine tune a model, which can be costly. You can just have an IDE, given prompt, given context, easily give you some output for that. So it can be useful if you don't want to run a full machine learning model. Just into prompt, it can give you some output. And it mainly useful for, because in our cases we are considering like small competitive programming problems, but it can be extended to real life software engineering problems, because it is directly put random problems directly related to the runtime of the software. So it may be used to measure the performance in regard of runtime of the software.
Okay, the last question, the last one. Did you envision some techniques to improve the performance?
Yeah, there can be some techniques like kindly use use promptings. That means there will be no further examples to classify the code, but there can be a way like few shot prompting or something like that. That means there will be some count X code and count code, and then asked to do the similar tasks. There can be a way. There are another techniques like chain of thoughts, like reasoning, giving the reasoning of classifying these particular programming, particular classes. There will be human input or something like that. That can be a way. Of course, current state of the art techniques are like fine-tuning model or something, doing something like that. There can be other ideas to extend the work. For specifically for prompting, there can be recent prompting technique like future prompting, chain of thoughts, adaptive prompting. That can be idea to extend, to utilize to extend this work, I think. Thank you.
Okay, thank you.
Yeah, thank you.
Thanks for the presentation. I had a question about the way in which you prompted Copilot, because technically you could say that big O is just the upper bound, but
upwards.
Did you try actually asking it for a tight upper bound or asking it for big data specifically?
Yeah, we did not do that, but interesting, we didn't present that finding paper, but it's a code generation model and it can actually give you some idea about that. Like, yeah, I asked for complexity and actually I asked for the, so it actually sometimes it inputs not only the upper bounds, sometimes it actually output the worst case scenarios, sometimes it gives some examples when it fails for the worst case scenarios or something like that. So that can be to check that out, but in our work we just only focus on the upper bound, but the output from this type of code generation model, or like chat style code generation model like ChatGPT or something like that, we can analyze their output, how they analyze the results. Like not only the upper bound, they can actually give you the worst case scenarios, they can give you average case of scenarios, they can give you which cases, some test cases where they actually fail for the particular classes or something like that. Reasoning for that, that can be up to for further investigation, I think.
I just have like two questions. So one question is that there have been a line of work on like static analysis, especially in the area, I think, on real-time systems. They want to ensure that the systems are behaving in a certain way. There's a guarantee. I wonder, like, have you tried like static analysis? Are they comparable with deep learning, maybe for some of the program that you have, or worse? So that's one question.
So did you ask to, we
Like,
compare the result with different techniques, but
like most of the technique here are machine learning based, but there have
yeah,
been like
yeah,
static analysis techniques that are designed
of
to
course.
compute the complexity of a piece of code. I wonder, have you
Okay.
had a chance to like maybe compare them?
Okay. Okay, we did not do that, but yeah, we can certainly check that out in your future work. Thank you for the suggestion.
Yep, I think it's good to compare with the future of work. It would be great if you can do
Mhm.
better. Maybe combine the technique together would be interesting. And I was
Yeah, of
also
course.
thinking, have you considered like, is there possible to ask GitHub Copilot like this code is search, but it actually you can do it in n log n, but it is like n square.
Mhm.
Can GitHub Copilot optimize code actually?
Yeah, so that is not part of the results, but in some of the case, you can do that actually. For my experience, actually, I am working in this particular area, so I can say that, yeah, you can do that. Like, you can give a prompt, like you can, there are some papers recently last year published in S&P, I think. So they actually repair the code with the GitHub Copilot. There is a code, you can give some suggestion for the static analyzer, you can repair the code. You can optimize the code by prompting, I think, but ChatGPT, conversation type models like ChatGPT or Bard, they can do better, I think. But of course, with the prompting, you can do, but that can be a different research topic, I think. But yeah, there's some work like program repairing with prompting. There's some topic like test case generation with prompting. Certainly, that can be the idea to reduce the complexity of a source code. Like there is a previously given example. This is binary search, but you have a linear search algorithm. You want to convert it to binary search. You can certainly ask GitHub Copilot with the prompting technique. It may give you the result, but it can be we can it can be a certain is a direction we think.
Thank you.
Thank you.
Okay, I guess here at least no visible lines. Over there online, and Andrea is already KO almost. It's 5 a.m. over there. So no. Okay, I would like to thank you again, the speaker,
Thank you.
Mohamed, for presenting and answering the question.
Thank you.
So according to the schedule, there is one last talk before the closing. So just little effort from everyone, especially over there. And this Fateme presenting, she said, I already see on screen. You can start sharing, your presentation with the help of Sajad here. The presentation is entitled Evaluating Code Comment Generation with Summarized API Docs. And Fatima is almost ready to go. Yes, we see the slides and we see online. So you can actually start. Thank you.
Okay, thank you everyone and good afternoon there. So it's midnight here. And I really just wanted to appreciate the organizers' effort to set up the camera so I can see the tables, and it's really good. It feels better not to really be online. It feels a little bit of being in person. Okay, so I'm going to present my student's work, basically Bilal's work, that he's my undergrad student who did this work for his undergrad research thesis. And that's basically the continuation of one of my other students who just defended his master thesis. And I'm going to talk about like a few background about what has been done previously and what led us to this code summarization technique. So the study that the problem that we are going to study is generating code comments automatically using deep learning models. It's been used a lot. It helps in program comprehension, like finding the helping the software maintenance and a lot of other studies. So Robin actually came with this idea that, okay, so you see two code examples here. We see the generated comments, like the comments that are provided for each code. We see the API that is used in the code. And then we also collected the API doc, which basically says, okay, what is the documentation for this API that is used within the function? So if you take a closer look at the API documentation and the comments, you see that in many cases it is very helpful, or even in some cases, the actually a few words from the API doc is appearing in the comments. So this led us to think about how we can use the API documentation to improve the code comments models, the generated comments for code comment models. So this was a published work in ICPC in 2021, which is called API to Come. So basically in that work, what we did was that we extracted the API, we extracted the documentation of the API also, along with the ASD and also the source code that was pre-processed. Then we put everything into separate encoders, and then using an encoder decoder stack, then we generated the summaries. So not to forget to mention that this was done using a transformer model. And interestingly, what we found was that as the number of APIs increases, the performance boost decreased. So it helped with some certain number of APIs, but at some point, and even in some cases, so it was negligible performance improved even when we use RNN-based models other than transformers, and this was pretty interesting. So we did a few other studies to figure out why this is happening. And we found that when there is, for example, only one API, then the performance is improving by more than 3 or 4 scores or 3 or 4 scores. And then when it is 2 APIs, it's helping. If it's 3 APIs, it's helping, but this improvement becomes less and less as the number of APIs increase. So we found that basically because sometimes the number of APIs are really high, it leads to, if you think about it, it's not helping the model anymore. It's basically adding some noise to the model. And one of the intuitions is that, okay, yes, there are many APIs used in some functions, but then not all of them are really important. Only some of them could be important and then could help or toward the intended functionality of the method. So this led us to think about 2 other solutions. The first one was ranking the APIs. So to figure out, okay, so if I have 10 APIs, how can I rank them and only use the ones that are really related to the work? That's another work that we presented a few days ago at ICPC called API Context to Come, which showed that this ranking along with the API description actually helped the model. The second idea was that, okay, so previously we found that when we have a lot of APIs, and these APIs are basically adding, when you consider the documentations, it's a long documentation that it's not helping the model. So we thought about, okay, how about we summarize them and then provide the summaries of these API docs to the model. So this is the work that Bilal has worked on. So basically the main question is that if we use text summarization techniques, can we improve the performance of the comment generation models? So we evaluated 2 summarization techniques, text rank and lex rank. that I'm going to talk about each of them shortly. But basically, first of all, there are a few summarization techniques. Some of them are extractive, some of them are supervised, some of them are unsupervised, and we don't want abstractive ones. So abstractive ones are the ones that when you give a text to a model, it just generates a summary without using, for example, important sentences. But then extractive summaries are the ones that it uses important sentences or important words from the given text, and then presents that as a summary. So for our purpose, because it's only API docs and we really don't want to change it, so we went with the extractive text summarization techniques. And there are a lot of techniques that are supervised or unsupervised, and we don't want supervised technique because then we didn't have labeled data sets, so we went with unsupervised techniques. And at the end, we came up with two well-known algorithms. These are not developed recently, but then these are very well-known algorithms, TextRank and LexRank. So the idea is that we take the API to come model, which I presented just previously. So which takes API documentations, ASTs, and also the source code. But then when we have the API documentations, we apply these text summarization on the API documentation before passing it to the encoder. So instead of passing a very long text, which is concatenation of all of the API documentations, we summarize those and then send it to the model. And then it's generally like encoder, decoder, and then it generates the summaries. So what we wanted to see here was that if we have, so first of all, can summarized API documentations improve the performance of the model or not? If it improves, how does it differ with different number of APIs? So let's say if I have 5 APIs, does it improve it better? Or if I have 10 APIs and so on? And if it changes text summarization technique, could it help in improving the model or changing the scores that are obtained by API to come? So as I mentioned, we use extractive approaches, which are also unsupervised, these two techniques that I'm talking about. The text rank is a very interesting algorithm. It just splits the text into sentences, and then the sentences are basically nodes of our graph. And then if there are overlapped words between these sentences, then it forms the links between those sentences. And then it applies the page rank on top of those that obtain graph, and then it gives us the important sentences and then represents them as the summary. LexRank is another variant of the PageRank, and again, it's a graph-based technique. So if we take a look at the data set that we had, in the x-axis, you see the number of APIs, and in the y-axis, you see the length of the words. So in the data set that we had, which is a Java data set of over 130,000 functions, there are some functions that had 39 APIs or so, but most of the functions had around 10 APIs with a few percentage going above that, which I don't remember the exact numbers right now. But anyhow, when we applied, so the blue graph that you see is the original text, and then the orange plot that you see is the summarized text lengths. And we see that after the 10 API, it is actually reducing the lengths of the API documentations when we apply the text summarization technique. So we hypothesize that, so basically it's somehow summarizing the documentations, and it's helping in reducing the number of tokens that are used as the comments, as the API documentations, and then it could be helpful. But when we applied the text rank and lex rank, we didn't see much improvement. I would say even some degradation, or it was almost the same thing. So in the first row, if you see, it's when all the APIs are used, so we didn't separate the number of APIs. And we use different variations. So API to come, as I mentioned, it had 3 different inputs. So ASD, API, and API docs. So if we use both ASD and API doc, then we apply text rank on it. It's almost the same result that you see at the second row. And even though if we don't use ASD, we just use API docs, and then the summarized version is still the same, almost the same scores that are seen here. So we applied it on different number of APIs also, and we found it only for 8 APIs. It is helping a little bit. It's not that huge, like it's not still that bad, but then it's not a huge performance improvement. And then as the number of APIs actually increase, you see that the model performance decreases so much. And so in case of, for example, 9 APIs, it helps a little bit, but then it's almost the same. The same results are obtained from LexRank, so it doesn't have much improvement. It's almost the same results obtained from the model without summarizing the API docs, and then the model with summarizing the API docs. And it was pretty interesting. So we did some investigations to see what is going on and so on. So we took a look at the actual API docs, and then the results that are obtained by text rank and lex rank. And we only looked into the informativeness. So basically, informativeness is capturing necessary identifiers to describe the functionality of the code, ignoring the fluency of the text. So if you look at it, look at these results, from the original one, text rank or lex rank, they are almost the same scores. So basically, even when we look at the informativeness of the summarized API docs, it doesn't change it that much. So it's basically a negative result that we obtained here. So I should mention that we only apply text rank and lex rank. These are not very recent text summarization techniques. We just summarized, and then we found that, okay, summarized API docs helps a little bit, but not that much. And in most cases, it produces the same results as the baseline. Something that we are thinking about is that, first of all, this is applied on transformer architecture. And maybe this is not the best way to impose a new information to the transformer architecture as a separate decoder. So we should find another way to impose it to the transformer architecture. And based on what I mentioned previously from the other work that we had at that we have as ICPC'23, which is working on the ranking of the APIs, we found that probably ranking is a more effective algorithm, like to find out which APIs are more important rather than just considering all of them and then apply the summarization techniques. But maybe a modified architecture could help the transformer model or even pre-trained models to improve the obtained result. Thank you. I think I'm out of time, right?
No worry. Thank you. Negative results are quite important. So thank you really for presenting your work. So there is anyone in the audience who want to make a question, like audience virtual and physical here? Yeah, you got Ali. Go ahead.
Yes, thank you for the interesting presentation. I had a question about your choice because you mentioned that you only used extractive, summarization and not abstractive. So
Yes.
if you were to choose abstractive, would that also not be reflected in the score, in the final score of your implementation?
So we didn't use abstractive because abstractive is kind of consider that you're reading a paper and then you're asked what is in that paper. You're not saying the exact words, but the synonyms. And in case of API docs, we don't want the synonyms. We want the exact words. That's why we didn't use abstractive ones. So we wanted to use exactly what is there in the API docs, not a rephrase of it, because it's technical and it should be the same. So that's the choice of between abstractive and extractive, and that's why we only use extractive ones.
Okay, thank you. That makes it clear.
Thank you.
Any other question? I'm a bit naive in the question, but did you thought to use generative model to augment knowledge on generate the summaries?
Can you repeat your question?
Did you thought to use, or did you think it would make sense to use generative model to generate the summaries? Like,
I think that's the same thing that's we just discussed. That's an interesting point. No, like we didn't use generative models to generate the summaries. And I think that's a good option probably to continue and see if that helps. But I still argue that that might or might not work. Because like if you take a look at this
yeah, I was
first
curious.
slide,
It was,
yeah.
you know, you investigate the topic, you for sure have an
Yeah, so candidate executable or like default button. So we want the exact things, not something similar to them. But that's an interesting topic that we might explore or audience could explore. Yeah.
Very good. Okay, so I think we can thank you again, Fateme.
Thank you.
Thanks a lot. I think, you know, we're going for the closing. I know that you are, you know, a little few minutes, you know, summarizing what happened. And I know that some of you are almost with the luggage to leave. This makes totally sense. But, you know, a few minutes and then we are free. Okay, the slides are visible. So I would like to, you know, shortly summarize or thank a few people that made this workshop happens, including all of you online and physically here. This workshop would not have happened or would have been so fun if not for your talk, for your effort and your questions. Let's see. We counted a bit of the participation, was quite, you know, turnaround of participant physically. If you see here, there were people coming and entering the room, you know, and for being part of the workshop. But there were also a round of participants that came online for presenting. That was quite nice. And also almost all people, you know, came with a question and in enthusiasm for presenting the talks. So thank you very much for joining us. And you know, don't give up over there since it's very, very late. I know it has been hard work. I want to thank you once more time. Maybe Albert will not be able to hear, but David can. Thanks very much for the keynote. Very inspiring and with many questions. It's not always, you know, happen, so I'm quite happy about it. The tool chair, which is really the groundwork, because, you know, these workshops, these really are focused on technology, data set replicability, and hopefully other people, know we mentioned before, could contribute a few new ideas for the future. But thank you very much for who did already this year. Of course, our web chair, you know, the nice web page, the video of the after the fact of the workshop will be available. You will be able to receive the talks if you want. And then we have to thank, of course, Arnaldo Squella, if you can thank him for the work. That's not an easy work. You know, we have a lot of demands and it's only one man show. So really, there is also the promo committee. We are quite happy. It was quite diverse this year, more than before. And, you know, without it, we cannot really review all this high quality paper, you know, go on. with the program. I also want to thank the Sajad and Christian from my team that helped on the organization. So maybe an applause to them. And being patient with me, because I'm very demanding time to time or often. What is more concrete for next year? What will happen next year? A few things. So for tools that have, were the best on the competition, there would be an invite for, a special issue, as you see in the slides. The call will open from November, right? And the idea is that, of course, the call is open to anyone, but for the tool that are invited, there is a delta that we will calculate from the original tool. The call is about natural language-based software to support software engineering processes, because the idea is that the tool have to have some innovation from the previous version. So you will hear from us. We'll post on social media so you can follow up. It's very important. For us now, it's a call to keep maintaining the tool and keep them available. One important thing, so the call is that they require, the tool accessible in Zenodo, so that is permanent. People can actually use and download and use for after. What's next? More generically, we are very interested to put more people together. We are try to engage people who came here. We already asked a few things. We'll follow up on that for people that can participate in a new challenge or create a new challenge. Of course, the idea that there are other communities that are around. We are not the only one talking about natural language for software engineering. We want to involve them. We had, a talk, a keynote from Copilot, from the creators. We want to have other participants join next year, probably targeting OpenAI. We are not the only one, I believe. We want to involve them. And the idea is that we try to move more toward topics that are important for software engineering, but also are moving and they are talked really a lot worldwide. AI language model is one of them. What is very important compared to last year to move the community forward, we are very open to new ideas, challenges. So if while hearing the challenge and the talk, you had got an idea on what could be a tool competition, I've seen classification user review, I've seen queries, with a gigantic data set. If you have an idea or data set available, just reach us. We're gonna coordinate for organize new competition to have this tool maintained, evolved over the time. Looking forward for your input. Said that, I think we can conclude. I think the very well, experience spent together, and I'm looking forward to see all of you in Lisbon, hopefully for sure for NLBSE 2024, right? And thank you very much again. And see you soon, all people there. We see in Zurich for celebrating a bit with a few beers, Luca, Andrea, and the others. Ciao, guys. Thanks a lot.
Yes,
Ciao, Rafael. Ciao.
Thank you a lot. Bye.
I think you really have a well-deserved rest gained. Ciao, ciao.
Bye, bye.
Bye.
Bye-bye.
Thank you. Bye.
Thank you very much. Good evening.